Alrighty, so here we are. This will be the last example of an integral in cylindrical coordinates, but it's a pretty good one. So buckle your seatbelts. So we will let E be the region of space that is inside of the cylinder x squared plus z squared equals to 1, and bounded on the right by the cone y squared equals to 4x squared plus 4z squared, and bounded on the left by the unit disk in the xz plane. Now, what is this cone, first of all? This cone, it doesn't look like the last cone that we saw. The last cone was z equals to the square root of stuff, right? This is y squared equals stuff. So the difference between this cone and the last cone is that it's going to open in both directions. So it's going to have kind of two sides to it. Okay, another difference here is that it's going to open in a sort of different direction. The last cone opened in the positive z direction. This cone is going to open in both the positive y direction and in the negative y direction as well. So, so that's good. We also are going to see we have this bounded on the left by the unit disk in the xz plane. I don't know about you guys, but that is screaming out to me to be the sort of polar region that we end up doing our polar outside double integral over. So I think we should probably take to GeoGebra before we go any further, though. We also have here this cylinder. It's like this unit circle in the xz plane, right? Just extended forever in the y direction. So let's take a look here at a picture of this region of space. So let's first put the cylinder down there. We have x squared plus z squared equals to 1. Notice that, we might want to zoom back here. Notice that this one opens in the y direction, right? I told you the y-axis was the green one in GeoGebra, which it looks like it is here. Okay, and let's add to that this guy y squared equals to 4x squared plus 4z squared. And okay, this is, I think we'd like to change the color on this so that we can kind of see it a little bit better. So that's a different color enough. That's fine. Okay. All right. So let's look at this region E. What are we talking about with this region E? So it's supposed to be inside this cylinder. So it's supposed to be inside this red guy here. And it says it's bounded on the right by the cone. So it's everything inside this red cylinder up to this cone. So it doesn't include the stuff that's, sort of inside the cone but past, or like past the cone inside of the cylinder is what I mean. That's not included. And it's bounded on the left by the unit disk in the xz plane. Well, that unit disk in the xz plane is the disk that is sort of bounded by the intersection of this cylinder with the xz plane. So we can imagine a circle going around there in the xz plane. That will be the left-hand bound. So we can just forget about the fact that this cone opens in both directions because we're not going to worry about this side back here. The left-hand bound of this region is this unit disk in the xz plane. So we'll cut it off at y equals to 0, right? Y equals to 0 is the equation for the xz plane. So it looks like this shape has rotational symmetry around the y-axis. So if I'm choosing to model this shape using cylindrical coordinates, I'm going to let y equal to y and let the polar coordinates be for the xz plane, especially since my left-hand bound here is this unit disk in the xz plane. That's modeled very nicely in polar coordinates, as in fact it is a polar box, right? So, so now that we've seen the shape, let's go back to the slides and see what's going on here. So Okay, so we've looked at GeoGebra. That was good. Okay, so we'll let y equal to y, and we'll have r and theta be polar coordinates for the xz plane. Now you have a little bit of a choice here, right? You have x. I'm going to let x be r cosine theta like it always normally is, or like we're used to it being. That's fine. And z is going to be r sine theta instead of y being r sine theta, right? So in particular, now our new sort of Pythagorean identity for polar coordinates is x squared plus z squared equals to r squared. We're probably going to make use of that somewhere. Right, in particular, this cone. Y equals to, if we just are looking at the right side, we can just solve for y and say y is the square root of 4x squared plus 4z squared. But then you can factor out a 4, and you'll get 4 times r squared underneath that square root. But the square root of 4r squared should just be 2r. So again, we have a cone that is in cylindrical coordinates written in this very nice equation where y is a linear function of r. That's very handy here. I think this should be a lesson that cones look very nice in cylindrical coordinates. So if you see a cone out there on the street or in the wild when you're allowed to go back out there, you might think to write that cone in cylindrical coordinates. So now here's our region E. So we'll write it in cylindrical coordinates r theta y, where y starts at 0, right? That's the xz plane. Y starts at 0 and ends at the cone 2r. And then we'll cover the fact that that intersection with the xz plane was just supposed to be a disk by getting this polar region here. We have r goes from 0 to 1, and theta goes all the way around from 0 to 2 pi. Oops. So then we can compute the volume of E by, again, integrating the constant function 1 over E. But we have to multiply by that Jacobian determinant R if we're going to use these cylindrical coordinates. And our first integrals with respect to y, which I love to do because that you just slap a y on, right? And then we have r times y, which we evaluate at y equals to 2r and y equals to 0 and take the difference. So we really just get 2r squared after the fact. And then we'll integrate 2r squared as r goes from 0 to 1, right? And that gives us what? 2/3 r cubed, which we evaluate at 1 and 0 and take the difference. Oh, this is easy, right? Then we just have 2/3, which we integrate with respect to theta from 0 to 2 pi. But that just gives us 2/3 theta, where we evaluate at theta equals 2 pi and theta equals 0. That leaves us with just 4 pi over 3. So that one was a pretty simple computation once we had the setup kind of worked out. But I think the setup was a little bit more awkward because it was cylindrical coordinates where we're using y as the coordinate that stays itself. Now, it's like you have that kind of freedom about cylindrical coordinates, but then with that freedom, you have to have a little bit of responsibility. So one thing that always helps is looking at the region in GeoGebra. And I think if you do that enough, you'll probably start to get good at not having to do that. But, you know, you might also try to draw a freehand too. That could be fun. Let's like sit back and look at maybe some big ideas here. So both of the examples that we saw here had regions of space that had rotational symmetry about one of the coordinate axes. And that's going to be the guiding principle. If you see your region has rotational symmetry about some axis in space, then you're probably going to want to pick cylindrical coordinates, or they could be a good choice to pick to model that region to do some kind of integral over it. And whichever axis is the axis of symmetry is the letter that you let remain itself, or the coordinate that you let remain itself in rectangular coordinates, and then take the other two and model that plane together as polar coordinates. So then we also saw some surfaces in this section having some nice equations in cylindrical coordinates. So we might sit back for a second and just think about some of our favorite surfaces and think about how we might model them in cylindrical coordinates. Because we're going forward now, we're going to get even more coordinates to think about in the next lecture, and they're going to be super important, but it's going to be easy for us to kind of get lost in the mix. So I think it'd be nice to kind of stop and breathe and record what some of our favorite surfaces look like equation-wise in these different coordinate systems. So we know what everything looks like in rectangular coordinates, but we can also just remind ourselves of some of that now. It's probably been a while. So in particular, a cylinder in rectangular coordinates had the equation x squared plus y squared equals to c squared, where c was the radius of the cylinder. Now we can do this in cylindrical coordinates, where z is equal to z, and x and y are given in polar. This just becomes then r equals to c. So r equals a constant. That's very nice. And we should expect that the coordinate system named cylindrical coordinates should model cylinders in the nicest way possible. Namely, one variable equals constant. That's beautiful. Love it. Okay, let's talk about the cone, right? We've seen this a couple of times now. So our favorite cone, z equals to the square root of x squared plus y squared, becomes z equals to just r, which we saw in, I think, example 1 of this talk. So again, I think other cones you can get as z equals to a linear function of r, or some other variable x or y equals to linear function of r. Those would be the cones that open in either the x direction or the y direction. So this is pretty nice. I think it's way nicer than this rectangular coordinate expression, z equals to r. So keep that one handy. Okay. We haven't thought about paraboloids in a minute, so let's think about those. Z equals to x squared plus y squared, right? That's the parabola that opened upwards in the z direction. Well, if we use cylindrical coordinates, that paraboloid has rotational symmetry about the z-axis, so we could let z equal z and x and y be polar coordinates, or x and y be modeled in polar coordinates. Then we get z equals to r squared. That's also pretty nice, right? Z is a quadratic function of r. So we might like having that one going forward in the future. And last but not least, maybe we'll talk about a sphere, which we've seen x squared plus y squared plus z squared equals c squared. This is a sphere centered at the origin of radius c, right? So it has rotational symmetry, I think, about all of the axes. So you can model this one with cylindrical coordinates in any of the 3 sort of ways of modeling with cylindrical coordinates. But I'll just pick the way where z equals z for now. So we get, again, r squared plus z squared equals to c squared. So this one is, I think this cylindrical coordinate equation is a little bit nicer than the rectangular one. It has one less thing squared in it. So that's nice. But, I mean, maybe it's not a shocker that the sphere isn't perfectly modeled with cylindrical coordinates. Which is why, when we come back in the next talk, we're going to meet spherical coordinates, which are super important, and they're also very nice to model spheres with. So stay tuned for then. But before then, I guess you'll take exam 2. So, do get at me if you want to talk about exam 2. So we'll see you.